Hi, my name is Mia Benavidez, and this is Newton's third law of motion, Part C. During Newton's time, experiments took place in small, private study rooms rather than big research facilities. He worked mostly alone using simple tools, candlelight, and handwritten notes. Without modern technology, he relied heavily on careful observation and mathematics instead of advanced equipment. His workspace was quiet, basic, and very different from the high-tech labs scientists use today. Newton experimented with simple, hand-built tools like pendulums made of metal spheres on strings, wooden frames, balance scales, and marked rulers. He judged motion and timing by eye or basic timers since precise sensors and digital tools didn't exist yet. Newton showed that when one pendulum ball hits another, the second swings away with almost the same force, while the first slows or stops. This demonstrated that every action causes an equal and opposite reaction, the core idea of Newton's third law. Challenges in Newton's experiments. Newton struggled to measure motion accurately because his tools were simple and timing was mostly done by eye. Heavy pendulum balls could become dangerous if something failed, and there was no safety gear. The handmade equipment had small flaws that affected accuracy, and factors like friction made results inconsistent. Without computers, he recorded everything by hand and did long calculations, making mistakes easy and corrections very difficult. Newton did intentionally design his pendulum experiment to show how motion and force transfer during collisions. He aimed to prove that when one object pushes another, it receives an equal pushback, supporting his third law. His results helped future scientists better understand motion, collisions, and energy transfer. Original benefits. Newton's pendulum experiments showed that forces and collisions follow predictable laws, proving that every action has an equal and opposite reaction. This quickly advanced physics by improving how motion and collisions were studied. Engineers used these principles to build safer and more efficient machines and structures. His work also sparked new areas of research in momentum and energy transfer that later influenced fields like astronomy and space exploration. Today's physics labs are clean, controlled environments with advanced safety and monitoring systems. Pendulums are built with precise materials and supported by high-quality pivots, while digital sensors, lasers, and photogates record motion with great accuracy. Computers instantly collect and analyze data, allowing scientists to measure speed, timing, angles, friction, and energy transfer far more precisely and reliably than Newton could. Modern benefits. Modern pendulum research improves our understanding of motion, energy transfer, and system stability. These studies support advancements in physics, engineering, and robotics, and are used in technologies like earthquake sensors, spacecraft navigation tools, and devices that harvest energy from the movement. Pendulum principles also help improve precision in electronics and everyday tools such as smartphones. Modern differences. Today's pendulum studies use lasers, sensors, and computer programs to precisely measure motion and collisions. Safety is prioritized with secure equipment, protective gear, and carefully designed lab spaces. Data is gathered automatically, and computers instantly convert it into graphs and reports, allowing for accurate analysis, easy sharing, and highly reliable results. Scientists plan to increase precision in pendulum experiments with better materials and sensors, even exploring motion at microscopic and quantum levels. These advancements could improve earthquake detection, navigation, robotics, and stabilization systems for satellites, drones, and tall buildings.
My name is Marisol Loza, and this is my presentation on Newton's third law of motion. Original process, lab environment. Isaac Newton's original lab environment was quite different from a modern laboratory. His lab was essentially a small private workshop rather than a dedicated scientific facility. He eventually later worked at his home in Worcester Manor during the Great Plague when Cambridge temporarily closed. There were no safety measures or standardized equipment. Newton often handled toxic materials like mercury and lead by hand. Lab equipment. Isaac Newton used a variety of simple but effective tools to study motion and forces. During his time, there were no advanced machines, so he relied on careful observation and mathematics and handmade instruments. Newton used mathematical instruments, rulers, compasses, protractors, used to make precise measurements and diagrams when analyzing motion. Experimental procedures. Newton demonstrated the idea behind rocket motion through a simple jet propulsion experiment. He used a small metal spear with two bent nozzles and filled it with water. When the water was heated, steam escaped through the nozzles in opposite directions, causing the spear to spin the other way around. This showed that when gas or steam is pushed out one way, the object moves the opposite way, an example of Newton's third law of motion. Newton's experiment proved that movement could occur even without air to push against, laying the foundation for the principle used in modern rockets. Original difficulties. Some initial hurdles. Newton faced several hurdles while experimenting with his early jet propulsion idea. One major hurdle was controlling heat and pressure. He had no modern tools to safely manage steam, which sometimes caused leaks or damage in his equipment. Safety issues. In the 1600s, there were no safety standards or protective equipment, so his experiments could be dangerous. When heating water to make steam for his jet propulsion experiment, the metal containers could overheat or burst, causing burns or injuries from hot steam or flying metal parts. Equipment issues. The metals glass available at the time were not very strong or heat resistant, so equipment could crack, melt, break, or easily during experiments involving heat or pressure. Information processing issues. Newton didn't have access to modern libraries or scientific journals. Gathering information meant reading rare books or corresponding by letter, which slowed progress. Original motivation. Original goals of the scientist. Isaac Newton's main goal with his jet propulsion experiment was to demonstrate how motion could occur through action and reaction forces, even without air or physical contact with another object. He wanted to prove that when one object pushes something in one direction, it experiences an equal push in the opposite direction, the basis of his third law of motion. This experiment was intentional. Newton carefully designed the experiment to test his idea about motion and forces, especially the principle that would later become his third law of motion. The people who were expected to benefit from Isaac Newton's jet propulsion experiment were mainly scientists and future inventors who sought to understand how motion and forces work. Original benefits. Immediate benefits. This discovery provided a clear visual example of his theories in action. It also gave other researchers a new way to think about propulsion and mechanics, inspiring future experiments that eventually led to engines, turbines, and rockets. Immediate advancements in this field. Newton's jet propulsion experiment immediately advanced the scientific understanding of motion and force, transforming physics from a field of observation into one based off of universal laws and mathematical proof. Immediate advances in other fields. Newton's focus on precise measurements in motion led him to co-develop calculus, a new branch of mathematics used to describe change in motion, a tool still essential in science and engineering today. Immediate advances in brand new fields. Newton's work linking gravity and planetary motion helped from the beginnings of astrophysics, a new field that applied physical laws to space. Modern process. The modern lab environment. Today, modern labs are highly organized, safe, and technology-driven spaces designed to allow scientists to conduct precise, reliable experiments. They are filled with digital instruments and computerized tools that allow scientists to collect and analyze data accurately. All procedures follow strict safety and ethical guidelines to protect scientists and the environment. Modern lab equipment. Modern jet propulsion equipments are far more advanced in control than Isaac Newton's early demonstration. Today, scientists and engineers use high-tech equipment, computer simulation, and powerful testing facilities to study how engines produce thrust and how air and fuel interact at high speeds. Modern experimental procedure. Engineers test how engines create thrust by measuring the reaction force of heat, force of air, or exhaust gases. A small jet engine or electric ducted fan is mounted on a thrust stand equipped with sensors that record thrust, temperature, voltage, and airflow. The engines run at different power levels while computers collect data on how efficiently it converts fuel or electricity into motion. Safety barriers, ventilation systems, and protective gear are used throughout the process. This demonstrates the need to stir a lot of motion. Modern differences. So modern advancements. Modern jet propulsion experiments have advanced through new technologies and materials. Scientists now use adaptive engines that change for better speed or fuel efficiency, hydrogen and electric propulsion for cleaner energy, and rotating the notion engines for stronger, faster thrust. Powerful computer stimulation and sensors make testing safer and more precise. These modern investments help create faster, greener, and more efficient aircraft and spacecraft than ever before. Modern protection and safety. Labs use strong protective barriers and remote control systems so no one stands near running engines. Researchers wear safety gear like fire-resistant clothing and ear protection. Fire suppression systems, ventilation, and emergency shut-off switches are always in place. Every test area is carefully monitored for heat, pressure, noise, and toxic gas using sensors and cameras. Modern information gathering. Scientists use digital sensors to measure temperature and pressure, thrust, and fuel flow in real time. High-speed cameras and laser systems capture how air, gases move through engines. All this data is sent to computers for instant analysis using powerful software and simulations. Modern information processing. Information is stored and shared digitally, allowing research teams around the world to collaborate in real time. This makes modern jet propulsion research faster, safer, and far more efficient than in the past. Modern benefits. Modern jet propulsion research provides many important benefits to science, technology, and society. It helps create faster, safer, and more efficient aircraft and spacecraft, improving global travel and space exploration. Other fields that benefit from the research. In transportation engineering, it leads to faster, more efficient vehicles and inspires new designs for airplanes, cars, and trains. In environmental science, it promotes cleaner fuels and reduces emissions, helping more transportation more sustainable. In material science, it drives the creation of stronger, lighter, and heat-resistant materials that improve engine performance and safety. Examples of technology spawn. Jet engines used in airplanes and aircrafts, which come directly from studying propulsion principles. Gas turbines used in power plants for electric generation, also involved from jet engine designs. Turbochargers in cars and trucks use similar concepts to improve engine power and fuel efficiency. Future expectations. Future goals for scientists. Scientists aim to develop an eco-friendly propulsion system such as hydrogen-fueled, electric, and hybrid engines that produce little to no pollution. Researchers are working on advanced rocket and ion propulsion systems to make space travel faster, cheaper, and capable of reaching farther planets. Scientists seek to create stronger, lighter, and heat-resistant materials to handle the extreme conditions inside modern engines. Potential benefits. New propulsion systems using hydrogen or electric power could greatly reduce air pollution and carbon emissions, helping fight climate change. Improved engines may allow planes and aircraft to travel further and faster while using less fuel. Next generation propulsion like ion or plasma engines could make deep space missions to Mars and beyond more realistic.
Hi everyone, I'm Kayla and I'll be talking about Newton's third law and how experience from studying it has changed over the law. To start, the original process was done in a very simple classroom setup, just a basic physics room with tables and open spaces, so students could run experiments safely. The whole idea was just to give students room to observe motion without anything getting in their way. Back then, the equipment was pretty simple too. Things like low friction carts, tracks, spring scales, or pulleys. The goal was to let students actually see how force acts in pairs. The basic procedure was straightforward. Set two carts facing each other, apply a force, and watch how they will push back with equal and opposite forces. Pretty simple plan fiction. Even though the experiment was simple, students still ran into a lot of challenges. One of the biggest issues was understanding that action and reaction forces act on different objects. A lot of students get confused and think the forces cancel out because they imagine them on the same object, but there was also safety issues. Moving carts, spring snapping, fingers getting pinched, stuff like that. Another problem was the equipment itself. If spring scales weren't calibrated right or sensors were off, it would throw off the data completely. And finally, even when data was collected, graphing and calculation sometimes went wrong because the unit mistakes or not accounting for friction. When scientists first started studying this, Newton's goal wasn't just to say objects move. He wanted to mathematically explain why things move, why they speed up or slow down, and how force interact. Newton intentionally studied motions and gravity because he wanted a system, a set of rules that could explain a lot of different physics situations. And the people who benefit the most were scientists and mathematics, who needed a clear model of motion. Eventually, social benefited too, through technology, transportation, and later on space exploration. Once Newton's third law was formalized, scientists could suddenly make much more accurate prediction about motion. In classical mechanics, this law helped build the foundation for how we describe almost every type of movement. After this, experience became much more persistent because now they could measure force instead of just observing motion. Other fields benefited too, like astronomy, understanding planetary motion became clearer because gravitational force also followed action-reaction pairs. And in brand new fields like space travel, predicting spacecraft motion is entirely based on Newtonian's laws. Today, the process looks really different. Modern labs include a lot more safety fixtures, things like eye wash stations, fume hoods, gloves, and advanced equipment. We now rely heavily on computers and sensors to collect data automatically. This cuts down on human errors and gives much more accurate results. Modern procedures also use written protocols that explain why steps and details, including safe checks and the expected results. Overall, the way we study forces today is far more precise because of technology. Modern differences. Modern advances. Modern labs use computerized data collecting systems, motion sensors, and high-speed cameras to measure force, acceleration, and reaction times with extreme precision. Physics now merges with fields like engineering, robotics, and aerospace, applying Newton's principle to advanced technologies such as drone and prosthetics. Safety is integrated into labs training. All experience must have risk assessments and emergency procedures documented before training. Collecting real-time data on motion, force, and energy replace manual reading. Captured collisions or movement too fast for human eye, allowing for frame-by-frame analysis. Programs like Excel, Python, and LabQuest analyze data instantly, graph trends, and compute event or error imaging. Researchers based on Newton's third law help scientists and engineers design faster, safer vehicles for cars and airplanes, rockets. It also helped understand motions and force, allowing for full efficient engines, electric propulsion system, and improved energy conservation. Other fields that benefit is environment science used in design with turbines, tidal generators, and other systems that harnesses natural force efficiently. Example is sports equipment. Tennis rackets and running shoes are using motion sensors analyzed for better performance and protection. Propulsion and motion control systems rely entirely on Newton's mechanics to maintain balance and directions. Researchers hope to apply Newtonian mechanics and modern physics to create clearer transportation, reducing carbon emissions from cars, planes, and rockets. It also helps understand and apply Newton's third law continues to guide space explorations, helping scientists design better spacecraft and plan missions to the moon, Mars, and beyond. Deeper understanding the universe by continued research into forces and motion will help explain how galaxies move, how gravity behaves, and possibly uncover new physics laws.
Okay, so this is the original process. So the lab environment, Newton's investigations weren't conducted in a modern lab, but in his study at Trinity College, Cambridge. He also used candlelight, quills, and rudimentary mechanical setups, often repurposing household items like pendulums made from pocket watches and ink bottles. The equipment he used inclined planes, pulleys, and spring scales crafted from brass and string. His action-reaction insights came from observing collisions between pendulum bobs and recoil in firearms, which means he also used cast iron cannons, gunpowder charges, cannonballs of varying masses, and rudimentary measuring tools like rope markers and pendulum timers. The procedures he used, Newton meticulously recorded the motion of paired objects, such like carts on tracks, and noted symmetrical forces. He also used water jets and air pumps to visualize reactive forces. Engineers fired cannons and measured how far the carriage rolled backwards. They varied cannonball mass and powder charge to observe proportional changes in recoil, which is a direct embodiment of equal and opposite reaction. Some early experiments used sled-mounted cannons on ice to minimize friction and isolate recoil forces. This setup prefigured modern frictionless tracks in physics labs. The original difficulties, they had safety issues. Newton's recoil experiments with firearms were risky as he reportedly injured his hand while testing force symmetry. He also had to worry about misfires, explosions, and flying debris. Engineers wore leather aprons and stood behind stone barriers. The equipment issues, friction and air resistance, distorted results. Spring scales lacked calibration and pendulums tangled easily. Cannon carriages warped from repeated recoils. Powder inconsistencies led to unpredictable force outputs. And without calculus, recoil was interpreted using geometric ratios and empirical tables. Engineers struggled to separate recoil from terrain effects like slope or mud. Newton originally aimed to explain motion symmetry. Military engineers wanted to predict cannon behavior for battlefield accuracy and carriage design. Newton's third law was formalized in principle, but cannon recoil had been observed for centuries. Newton gave it theoretical grounding. The beneficiaries, artillery units, shipbuilders for naval recoil management, and eventually physicists studying momentum conservation. The original benefits were cannon recoil provided one of the earliest empirical validations of momentum conservation. When a cannon fires a projectile forward, the backward motion of the cannon itself proves that momentum is exchanged and not lost. Naval engineers on ships, cannon recoil posed a serious threat to stability. Engineers developed rotating gun turrets and recoil sleds to prevent damage to wooden decks. These innovations later influenced the design of rotating radar dishes and satellite mounts. And then in some new fields, ballistic science, the cannon recoil experiments evolved into the balance of ballistics, which is a study of projectile motion, impact, and force transfer. This field now supports everything from forensic science to space probe launches. Modern process lab environment. Today, ballistic labs are climate-controlled, vibration isolated, and often underground to eliminate external interference. These labs simulate cannon recoil using precision sleds, robotic mounts, and high-speed sensors. They use recoil sleds, which are mounted on low-friction rails. These sleds measure backwards motion with millimeter precision. They're equipped with strain gauges, accelerometers, and piezoelectric sensors that detect force spikes in microseconds. They also use high-speed cameras capable of capturing 100,000 frames per second. The procedures they use now are experiments simulating walking, jumping, and robotic grasping. Data is collected in milliseconds and analyzed using vector calculus. Some of the modern differences in the advancement, modern cannons are designed with recoil management in mind. Hydraulic recoil buffers absorb shock and redirect energy, minimizing wear and improving accuracy. Some recoil systems now use magno magnet I'm sorry, I'm not going to pronounce that right. Fluids, which are liquids that change viscosity in response to magnetic fields to dynamically adjust damping during firing. Some of the protections: cannons are often fired remotely to protect operators. Recoil is monitored via telemetry, and emergency shutdown protocols are built into the system. Recoil testing chambers are reinforced composite materials and shock absorbing floors to contain energy and prevent ricochet. Recoil data is collected from multiple points, like at the barrel, mount, projectile, and synchronized using high-speed data buses. Modern benefits. Satellites use spring-loaded or gas-powered mechanisms to eject payloads. The recoil must be precisely managed to avoid destabilizing orbit. New technology spawned. Skyscraper dampeners were inspired by recoil systems. Tuned mass dampeners in tall buildings counteract wind and systemic forces by pushing back, which is a structural embodiment of action-reaction. Advanced prosthetics use Newton's third law to stimulate natural movement. When a user pushes off the ground, the limb reacts with calibrated forces. Some of the future expectations, future goals, neural recoil interfaces. Future prosthetics may use brain signals to predict and respond to recoil in real time, creating seamless motion. Zero gravity recoil management. In space, recoil behaves differently. Engineers are developing systems that absorb and redirect force without relying on gravity or friction. And some of the potential benefits are seamless motion. By predicting recoil before it happens, the prosthetic can preemptively stabilize itself. This allows for smoother, more natural movement, especially during high force tasks like jumping, lifting, or throwing.